Hello, this is Dong-Soo from the Applied Superconductivity Lab. Today we will learn about the cryogen consumption for cooldown. It is about how much coolant is needed to cool down the magnet. In this lecture we will define and discuss two different cooldown modes, perfect cooldown mode and Dunk cooldown mode, with their cooldown mode equations. Then, we will conclude this lecture with the cryogen volumes tables required for cooldown to optimize cryogen consumption. Perfect cooldown mode is an ideal cooldown method that uses the coolant's total 100% energy or enthalpy to cool the magnet. This method is not practical in real-world problems but enables cooldown in a significantly specific condition. The perfect cooldown mode involves a series of integrations between the magnet's copper layer and liquid helium, which results in a perfect energy exchange to cool the magnet. In the equation, we put the specific enthalpy of helium because this equation was based on liquid helium. However, different liquid coolants, such as liquid nitrogen and liquid neon, can be applied to this equation. The specific enthalpy of helium of 4.2 Kelvin indicates that we are dropping the external temperature 300 Kelvin for instance until the temperature hits the bottom temperature, 4.2 Kelvin. Then we consider the required amounts of coolant that we use to drop the temperature to 4.2 Kelvin to cool down the magnet. Dunk cooldown mode is a practical method in which we dunk or submerge the magnet at a specific temperature into the coolant, in this case liquid helium. Dunk cooldown mode is less efficient but easy to implement, so many magnets use this method in many cases. The equation shows that the magnet, with an initial temperature higher than that of the liquid helium, is cooling down to 4.2 Kelvin. The specific heat of vaporization, HL, indicates the heat energy of the vaporized liquid helium, due to the magnet's relatively high temperature than the lower temperature of the liquid helium. Finally, this cooldown table shows the required amounts of cryogens or coolants to cool down the magnet until the target temperature. Given the coolant's boiling points, using multiple coolants sequentially to minimize cryogen consumption is favorable. For example, as shown in the table, if we use liquid helium LHE to cool the magnet at room temperature 300 Kelvin, we use a large amount of liquid helium of 30,000 liters if we consider the dunk mode. Instead, the coolant consumption of liquid helium can be reduced by using 460 liters of liquid nitrogen to pre-cool the magnets from 300 Kelvin to 77 Kelvin. Then we use liquid helium for temperatures below. Also, given the high cost of liquid helium, we need to reduce the consumption as much as possible, so if we control the liquid helium in the ideally well-controlled system using the perfect system, we can drop the magnet temperature to 4 Kelvin with just 150 liters instead of 2,100 liters of liquid helium. Here is the summary of this lecture. First, the perfect cooldown mode uses the coolant's total enthalpy to cool the magnet and integrates each specific temperature range in a series of perfect heat transfers between the magnet and the coolant. Second, the dunk cooldown mode submerges the magnet at its initial temperature in a bath of coolant to lower its temperature until it reaches the required temperature. Also, there is a two-step procedure for cooling the magnet using liquid helium. First, we cool the magnet until it reaches 77 Kelvin using liquid nitrogen, and then we use liquid helium immediately for temperatures below 77 Kelvin. This procedure is significant because it is crucial to reduce or optimize cryogen consumption.